And everyone, when they come to ISOLDE, they say that this is interesting because here we can understand many things.
We want to probe the really exotic nuclei.
ISOLDE has a range of beams available and isotopes which nobody else can provide.
So you have mechanical engineer, technicians, people that are designing the target, that are operating the targets, you have the physicists, and all those persons that are actually managing to collaborate.
The ISOLDE physicists had been waiting for this upgrade for more than 10 years.
Hello everyone out there on Facebook. I'm Sarah Charlie. I'm a science writer working here at CERN, and we are coming to you live from the ISOLDE control room. Right now it is about 2:08 in Geneva. So ISOLDE is one of the oldest running experimental facilities at CERN, and unlike the LHC, it works with atoms. So what we're going to be discussing today is what type of research is happening here and what are some of the applications. In just a few moments, we'll be having Erwin, who's the guy who's responsible for making sure this whole thing runs, coming on. So we'll be right back with Erwin in about 20 seconds. All right, and we're back. So we're here with Erwin. So while we're chatting, feel free to type your questions into the comments. We'll have a live feed of them. I'll start with a few of my own, and then we'll go right to the Facebook audience, see what you want to know about it. So Erwin, ISOLDE has been here for 50 years, right? It's its 50th birthday actually today.
50 years today, yes. And thank you for the nice introduction. Of course, I'm not doing this all by myself here, running the machine. We are with a very competent and very dedicated team of engineers making the machine run on a daily basis, as well as a lot of support from all the different departments at CERN.
So you're making this machine work, but what is this machine? Like, what does ISOLDE actually do?
ISOLDE is a facility at CERN where we actually produce rare radioactive isotopes. And these radioactive isotopes, they are then being sent to different experiments that cover large areas of the nuclear physics.
So what is a radioactive isotope? Like, can you walk me through what you're actually working with?
Radioactive isotopes are actually brothers and sisters of their stable element, if you want. You know the elements of the that you have learned at school. You know, iron and lead and oxygen, helium, all of those. Those that are around us in the world, they're all stable, as we call them. But an isotope or a radioactive isotope is one that has too many or too little neutrons in its nucleus, and that makes it interesting because they all have a certain half-life. It means they will not exist forever. Some they live for many years. Some others, they actually decay in just a few milliseconds.
Okay, so like if I were to look at the periodic table of elements, which we all know about, where would these isotopes sort of fit into that?
We can make isotopes from actually almost every element.
Every element?
Here at ISOLDE, many elements, yes. We have about 1,300 isotopes that we can make. And what we do with them is actually we send them to these different experiments, and there you must think about nuclear physics in all sorts of areas. So if we look at the material science, for instance, you know, people are investigating different sorts of materials which can lead actually eventually to better semiconductors, for instance, for faster computers, more reliable computers. Also for biomedics, we do things here which actually can give you a lot of insight in what could be better treatments for cancer in the future. And if we look at the larger scale, we also look into questions like the astrophysics take care of, in what actually happens in the stars in our universe.
So ISOLDE is really able to look at basically how stuff works in all these different areas. But I had another question. So I hear a lot about CERN and high energy physics and particle physics, but as I understand it, ISOLDE is actually low energy nuclear physics. So how is this low energy nuclear physics different than the high energy particle physics that we hear about a lot?
It is quite different. You could compare it with perhaps a microscope, whereas we don't zoom in as deep as the LHC, for instance, does. We stop at the level of atoms. That means we are looking at matter as such, where you have the nucleus, with its neutrons and protons in it, and with the electrons still going around it. So the properties of these elements actually still, like the chemical properties that the actual element has. And we don't go down into the very, very smallest bit, like at LHC, where they collide protons with each other and they really go for the absolute smallest what's in there. So that's quite different.
Okay, so it's a little bit like with something like the LHC, you're able to look smaller than the proton,
Yes, yeah.
whereas with ISOLDE, you're able to zoom out
Yeah.
and look at how these protons and other neutrons and what they're capable of doing.
And then specifically they're radioactive isotopes, so they're the brothers and sisters that don't exist on the Earth anymore. That makes it really interesting.
Oh, that's quite cool. So you're making things that we literally cannot
We don't have
find
them
on
anymore.
Earth.
No. Well, some of them still exist that have a very long lifetime of, 70 million years or so for the uranium. But yeah, the short-lived stuff, it doesn't exist simply.
Okay. So I've seen that you've actually been working here at ISOLDE for 14 years.
Yeah, it's a long time.
It's
yes.
a long time,
Yes.
yeah. So it turns 50 today. You've been here for the last 14 years.
Yeah.
What makes you want to, keep working here and keep coming back to work day after day?
Well, it's a very very interesting facility, of course. It actually goes back to the history of mankind, one could say, in the long gone past, where alchemists were already, trying to figure out how can we make gold out of lead. And if you go back to those days, we have improved quite a bit on the knowledge we have, of course, ever since. Here at ISOLDE, ISOLDE started on the synchrocyclotron in the 60s, in 67 actually, when we did the first beam, 50 years ago now. And luckily, actually, at the end of the 80s, when the SC closed down, the directorate and the Director General, Carlo Rubbia, at the time, they understood that it's a very promising and very facility with a lot of potential. And they decided to move it to where we are now, connected to the booster. And from the booster, we take the 1.4 giga-electron volt protons, and we take about 50% of all those protons. So we are, a significant user at CERN, if you want. And what makes it really interesting here is the diversity. We have every week a target change. We have many young people coming from all different universities, from many different countries. Because ISOLDE is a collaboration within CERN, we also have people coming from countries that are not CERN member states. So we had this year, for instance, a team from South Africa. And every time we learn something new here, new questions pop up. So there's never a dull moment.
So it's really diverse, and it just keeps
on
expanding
learning.
and continuing.
Yes.
So if you have any questions, feel free to write them on Facebook. Shout out to Arno, who's watching. How's it going? So let us know that you're watching. Let us know what you want to know. We've been chatting with Erwin, and we are going to cut out, or we're going to leave for about 30 seconds, and we'll bring on our next guest, Magda, who is actually a scientist who gets to play with some of these particles that Erwin and his team help produce.
Yes.
All right, so thank you so much, Erwin, and we'll be right back
you.
with Magda. All right, so we're back here with Magda. If you have any questions as we're going through this Facebook Live, feel free to type those into the comments. We'll try to get to as many as we can. Also, feel free to say hi. We'll be able to see it live. So here with me is Magda, who is actually one of the scientists who gets to play with these particles. So Magda, you do low energy physics. Can you tell me a little bit about what low energy physics is?
Low energy physics is the physics that you can do with low energy beams. And now the type of experiments that you do will let you reply to questions in nuclear physics, in astrophysics, what Erwin was already mentioning, and also in some applications. Now the tools that we have come very often from atomic physics. This is what I really love about this facility, that you're really combining fields. You're using lasers to excite the radioactive isotopes. You might be trapping them in ion traps to let them revolve for many milliseconds or seconds to see, for example, what their masses is. You might also look at their decay. So you take the beam from ISOLDE, you implant it into a small sample, and you have many detectors for beta, gamma, and other radiation around them. And you just look at what the properties are.
Okay, so you're actually able to So you make these using the beam, right? So you make these rare elements these rare isotopes that don't exist on Earth.
Exactly.
And then you're able to sort of trap them and study them, right? And look at what they do and how they perform.
Exactly. And in some experiments you do it for longer, and some you just wait until they quickly decay.
So what are some of the things that you've learned about atomic nuclei and these rare radioactive isotopes that you've been studying?
Quite many things. You know, in 50 years we have gathered a lot of knowledge, and ISOLDE, because we have high intensity and also good quality beams, we are able to refine the answers to some of the questions that have popped up. So I give you one example of very light nuclei. We call them halo nuclei because they are a little bit like the halo on the saint's head. You have a few protons and neutrons which are very close to each other in the middle, and you have usually 1 through 2 neutrons which are orbiting far away. And these were discovered, but we did not know what their properties were. And thanks to studies at ISOLDE, we know now that these nuclei are not deformed. They're actually quite spherical. They're very nice, let's say, spherical balls, but they have these 2 or 1 neutron very far away from the rest. And this we didn't know before.
So neutrons can actually orbit an atomic nucleus like an electron can.
Of course, not that far away, but yes, indeed, further than one would have thought.
Okay, so what do these nuclei actually look like? Because I always assumed that you have an atomic nucleus and it's just sort of this hard, packed, you know, balls just packed together into the nucleus. But do they actually look like that, like the chemistry textbook picture?
Well, they are hard balls indeed, because they are much smaller than the electrons orbiting them, yet many of them are spherical. However, there are many which are deformed. So often they look like rugby balls, they might look, let's say, like gherkins, and they are also rotating because they are not spherical, they can rotate in different dimensions. There are even some which have so-called octuple deformation, which means that they are shaped like pears. And Liam, who is with us, he was actually studying one of them for his PhD thesis.
So you can actually make these nuclei that look like pears.
Yeah, there are some of them, not many, but the most exotic ones are indeed, they look like pears.
Okay, so you're making these new atomic nuclei that are unstable, they decay quite quickly. What are some of the applications that you can use these for?
Well, they're really nice. So I like 2 of them, which would be biology and medical physics. In biology, actually, my own project is connected to that. Some of our colleagues, for example, come here to study the toxicity of metal ions. So let's say mercury. We know that it's not good to inhale or to swallow mercury. However, we don't know very well how the toxicity works in a microscopic scale. They come to ISOLDE because it's very easy to detect radiation. So, you know, instead of injecting milligrams of mercury and combining it with your protein or DNA, you come to ISOLDE, you put maybe 1 million atoms at a time, you put many gamma detectors or other radiation detectors around, and from that you try to, or you actually learn how the mercury is binding to the biomolecules.
Okay, so you can actually watch it as it moves because it emits this little tracking signal, essentially.
Exactly.
Okay, so you can learn a lot about how this toxicity actually works in humans.
Yeah, so this is,
Okay, we have a question from Arno on Facebook. Arno asks, Magda, could you please tell us a little bit more about the Xavier of Life and the Philosopher's Stone? So it looks like we have a little bit of a Harry Potter reference here. What are some of these things that you're doing with this?
Well, I would say the elixir. One of the things is to use all the target. For me, this is the elixir of life because this is what gives us all the isotopes that we have. Erwin mentioned that there is over 1,000 of them. So maybe it doesn't look that fancy and it's quite heavy. So one person has a hard time moving it. But this is where we're really creating all the isotope. What else? And I think the other things would be all the detectors that we are using.
So we've got another question from Facebook. This one comes from Ryan. He writes, what control systems are required in ISOLDE? Does it need a vacuum or humidity control? So how do you control this experiment?
Vacuum is the key word because these are low energy experiments. That means that the beam will not go very far if you leave it alone in air. So that's why everything that we do, all the ions are enclosed in vacuum chambers. I think this is the main part. Then humidity is also important so that things don't get rusty and maybe they don't stop working. And this is what Erwin knows a lot about, how to make the air conditioning humidity control systems work.
Okay, we've also got a question from Christina. How do you produce the isotopes that you work with? So walk us through the process a little bit.
You have the protons that are coming from one of the CERN accelerators. This is the reason why we are at CERN. Then these protons are hitting the what I call elixir of life. So this would be our target, which we can see now in the animation. It's usually a rod, maybe 20 centimeters long, which is filled with material. Very often we use uranium because this is a heavy element, and you can imagine if you manage to split uranium, you will get out many different chemical elements. But sometimes it might be even a calcium target if you want some specific isotopes. These are, as was shown a moment ago, they are created in this target, and they have to get out so that you can do research. So what you do, this target is heated to up to 2000 degrees so that these different chemical elements or these isotopes have a chance of evaporating and getting out.
So it's a little bit like a tea kettle. So you make
Exactly.
the isotopes in there, then you heat it up, and then they essentially go out the quote-unquote spout.
Exactly.
And then they can go into your experiments.
Almost. Then you still have to ionize them because they are neutral
right.
atoms, so which are not so easy to control. So very often you're using lasers that sometimes you can see in the animation from neutral atoms to get ions. And this is when you can start manipulating them. Like now we can see a magnet which is bending the different isotopes, and the magnet can choose the mass in which you are interested. My thesis was on magnesium 31, so that we set the magnet to mass 31, and this is the beam that we got in the experiment.
Okay, and that's how you can isolate all of them as they go through. So you can pick a specific isotope to study.
Exactly.
And you're not getting a whole bunch of isotopes in there, confusing results. We have another question from Julie on Twitter. Julie writes, can you tell us about what ISOLDE is doing with medicine?
With pleasure, because I think this is relevant for many of us, not only crazy physicists. So in medicine, we are trying to produce new radioactive isotopes which were never used in medicine before. In the hospitals these days, you have small cyclotrons which can produce isotopes for diagnosis, but also for therapy, for example, for cancer. And at ISOLDE, since we produce so many of them, we try to specialize in those that you cannot produce in hospitals. So one of them is terbium. There are different isotopes. Some of them you can use for diagnosis in medical environment and some for therapy. So there is a new word which is quite in fashion, is theranostics, doing therapy and diagnosis at the same time. And that's what we try to do, to send it then to hospitals for the first trials. And if this is successful, we're sure there will be a startup company who can produce it.
So you can use radioactive isotopes in medicine. Is this something that has already been done? Are there any risks involved with it? Normally we hear the word radiation, we think like, oh, radioactive elements, I don't want anything to do with that. But it sounds like you can actually use these to heal people.
Indeed. And of course, you act with anything, you have to be careful. It's just you're driving a car, as you've heard recently, okay, cars might be dangerous as well. You might use it for different purposes. With radiation, of course, in medical environment, you want to be sure that this will not harm. It's all about the dose. You know, many different things will not, kill you or harm you if they are given in the right dose. So this is why the radioprotection checking and also, other medical checks are very important. And radiation has been used already in many different applications. In positron emission tomography, we've been using radiation and antimatter, which might also scare some people. We are using, for example, when you have your thyroid, which is too active, then you also swallow radioactive iodine, which will then lower the activity of your thyroid. So it has been used, and I hope it will be used in the future.
Okay, well, that's great. So Magda, just to summarize, she works here at ISOLDE. She's working on some medical applications using these radioactive isotopes. What we'll be doing next is we'll be chatting with Liam, who's working on a new upgrade to ISOLDE. So Magda works on low energy physics. We'll be chatting with someone working on high energy physics. Remember, if you're tuning in, feel free to type in your questions, your comments. We'll try to get to as many of them as we can. So thank you so much, Magda, for joining us, and we'll be right back in 30 seconds with Liam. All right. Hey, everyone. Thanks for coming back and joining us. Remember, keep asking us questions on Facebook, any comments, or just type in to say hi. Right now, we're here with Liam, who's a scientist who's working on a new upgrade to the ISOLDE experiment called High ISOLDE. So we're just chatting with Magda about low energy physics and how they can make new isotopes that could have potential medical applications. What is High ISOLDE, and what are some of the applications that could have?
So at High ISOLDE, we actually take the same beams that Magda uses, exactly the same beams, but this time what we want to do is we want to increase their energy. So Magda wants to transport the beams and to implant them in different places, watch the decays, maybe trap them. What we want to do is we want to accelerate them to high energies and make nuclear reactions now. So we want to use these exotic radioactive beams to make nuclear reactions. So with that, what you're able to do then is you're able to make exotic reactions which happen in stars, or you're able to study fundamental nuclear physics properties by studying how the reaction proceeds.
So are you actually able to replicate the processes inside stars?
Yes, well, we produce really we produce the same reactions that happen inside stars, or very similar reactions, and we try to map out the pathways which cause the very heaviest elements to be produced, for example, in supernovae, where you can collide two nuclei, fuse them together, and you can progressively increase the mass and the element number of the things inside the star.
So you're just trying to figure out where everything comes from.
Yeah, it's pretty much the question of what we're all made of, exactly. Yes.
So for instance, I think I learned somewhere that within a star you can make up to iron. That's the heaviest element you can make in massive stars. How would you make something like gold, for instance?
Yeah, these very heavy elements, they go via very exotic pathways. So if you think about the numbers of protons and neutrons inside the nucleus, when you have very neutron-rich nuclei, so lots and lots of neutrons, and you make reactions on those, you go along what's called the R process path, where you rapidly capture a lot of neutrons within inside the star. And this can happen in, for example, supernova explosions or collisions of neutron stars, things like this, where you can rapidly add lots and lots and lots of neutrons up to make very, very neutron-rich nuclei, which then decay back down to then the heavy elements that we see.
Okay, so you're not actually making gold immediately. You're actually making something that has a ton of neutrons in it, and then you have this big unstable ball of neutrons, and it itself decays into something like gold or platinum or these heavy elements that we see.
Exactly. The reactions happen on very, very short-lived exotic nuclei that we don't see usually in the lab, so we have to come to somewhere like ISOLDE to reproduce those reactions, and it goes in many, many steps.
Okay, what can you learn? So you said we can learn a lot about what happens during supernova, we can learn about what happens when neutron stars collide. What are some of the things that you've actually been able to learn through this ISOLDE research?
Well, aside from the astrophysics part of the things, we're very interested in fundamental physics, particularly in fundamental nuclear structure physics. So how these particular numbers of protons and neutrons combine, how they interact, and how they stick together, what are the forces involved in binding these nuclei. So Magda mentioned shape also. It's one of the things that we study a lot with the reactions at high energy. We like to study the shape of nuclei. And we were able to discover, or at least observe, very kind of exotic shapes which you don't see in the stable isotopes. So, for example, the pear-shaped nuclei that Magda mentioned only occur in exotic radioactive isotopes. So you can't study them in a normal way. You have to come to somewhere like ISOLDE to produce such an isotope in order to study it.
Okay, so we've got a question from Lee on Facebook. Lee asks, why do we care about what happens in stars?
It's a good question. I care a lot about what happens to stars. I want to know where we came from, what we're made of, and it's a very fundamental question that how do we see all these elements, like you say, beyond iron, and we're all made of atoms, and all these atoms we know were produced inside stars and exotic astrophysical processes. So it's just a fundamental question of why are we here, or how are we here?
So short answer, because it could explain almost everything. I guess that's what you were saying. We also have another question on Facebook from Nedemes. Nedemes asks, what will be the medical applications in the near future from high ISOLDE? So we know that Magda was working on medical applications, but could high ISOLDE also have medical applications?
With high ISOLDE, we're focusing more on the fundamental physics side of, and in terms of the high energy, but the acronym actually is high intensity and high energy. So the other part of the project, there's in two components, intensity and energy. So the intensity part will help us upgrade the energy and the intensity of the protons that we receive on the target, which could help us produce higher quantities of the most exotic isotopes, or even some isotopes for medical physics, where the quantity just aren't enough yet. The intensity upgrade could bring us into a new regime where we're able to produce new, very useful, very clean medical isotopes.
So it's much more fundamental. It's just this hasn't been explored yet. We're pioneers. Let's go out and see what we can do.
Partly, yes. Partly this, yeah.
So we've got another question from Facebook. This comes from Rob. Rob asks, what is the shortest lived isotope measured at ISOLDE? So what are some of the timeline, like lifetimes of these particles?
It depends on what you want to do with them. So high ISOLDE, where I'm interested in, first, to get them to high energy, we have to trap the beam that comes from the low energy part, and we collect it up so we have a bunch. And that bunching process and the subsequent charge breeding process, where we have to strip more and more electrons off in order to accelerate the beam, takes of the order of milliseconds, 10 milliseconds or hundreds of milliseconds. So we're limited if we want to perform reactions to isotopes in the millisecond or second range at the lowest. But indeed, if you want to go to very exotic nuclei with very short half-lives, for example, measuring masses of isotopes, which you do with the low energy beam, you can go all the way down to 1 millisecond or sometimes, well, about this order, about 1 millisecond lifetime.
Okay, and so are these really short-lived nuclei? Are these the ones that have the weird-looking shapes that you're talking about, like the pear? And I think I saw one that also looks like a banana.
Yeah, well, actually, the lifetime is more indicative of how exotic it is in terms of the numbers of protons and numbers of neutrons. So the more neutrons you add or the more neutrons you take away, generally the shorter the half-life gets. The exotic nature of the shapes comes more about the specific combinations of protons and neutrons. So just like the electrons have a shell structure in atomic physics, the protons and neutrons inside the nucleus also have a kind of shell structure where they orbit around and have. So if you can choose exactly the right combinations, you can have closed shells or open shells of protons and neutrons, which then lead to these exotic shapes.
So even within the atomic nucleus, you have the same isotope with the same number of protons and the same number of neutrons, but even those can look different from each other just based on how they decide to arrange themselves.
Exactly.
Okay, wow, that's so cool.
Yes.
So you can just make all sorts of shapes by exciting these different combinations.
Different excitations, or different changing just the numbers of neutrons or just numbers of protons, yes.
Great. So thanks so much for chatting with us, Liam. So we're going to go and take a quick 30-second break, but when we come back, we're going to be doing a live Q&A with all of our scientists. So while we're away, just quickly type in any questions, comments, anything you want us to talk about, and in 30 seconds, we'll try to get to as many questions as we can. So stay tuned. All right, so we're back with our three scientists and our engineer, Erwin. So we have Erwin, Magda, and Liam. They're all working on slightly different things here at ISOLDE. So our first question from Facebook, it looks like several people have been asking if there is a link between gravitational waves and what is being done at ISOLDE.
Should I try? Well, I see people are following what's happened in the Nobel Prize committee recently. For sure, gravitation is important in the nuclei. All four forces of nature play a role. However, gravitation is the weakest one in nuclei, unless you have a neutron star. This is where you don't have the electromagnetic interaction because the neutrons don't have electric charge. And this is where, of course, gravitation takes a big role. So to my knowledge, I would say when you're studying astrophysics, maybe neutron stars, this is where such things will be important. In nuclei, when we look at nuclear physics, I have a feeling we rather neglecting the nuclear for the gravitational force.
Yeah, indeed, we're neglecting the gravitational force, but we're somehow studying the same type of events, let's say, that happen. Maybe in a neutron star collision, you have a lot of nuclear reactions which are producing, like I said, the isotopes, the heavy elements. So we're kind of looking at it from very different angles, but somehow it's complementary.
So you're taking a very tiny laboratory perspective, a couple atoms, seeing how they react, to some much larger cosmic events like supernova. Just a follow-up question, because I know that LIGO won the Nobel Prize for black hole, seeing two black holes collide in gravity waves from that. Can you do anything with black hole research, or is that completely different?
Oh, good question. Well, I would suggest not, but I would suggest maybe not so directly related with black holes colliding, but
So much more on the supernova neutron star side, and
Yeah.
much less on the black hole side. That's something completely
a
different.
little bit less exotic.
A little less exotic. So we have another question from Facebook. What can nuclear research teach us about nuclear power?
Okay, what our colleagues are studying very often is the detailed processes that are taking place in nuclear reactors. So even though we know quite well about nuclear fusion, about fission, and now also about fusion, there are certain things like exact half-life or exact amount of heat which is getting out from the nuclear processes inside the reactor that are not necessarily very well known. So I know some of the techniques, such as absorbing all the gamma rays and all the beta decays from a nucleus, they help us in figuring out exactly what is the amount of heat. And of course, this is important when you are planning such reactors, and also when you're running a reactor. You actually want to know when will it heat, and how much cooling, for example, do you need to cool it down. Second thing would be also predictions of how long will the radioactive waste live on. We're all trying, of course, to reduce it, to make it the smallest impact possible, and some of our studies also contribute to that understanding.
Because here you're able to look at a range of isotopes, how long they live, what types of byproducts they produce. So you're basically making, the periodic table of isotopes, and learning about what all these different elements that, exist in stars, that might be produced on Earth, in nuclear power, how they behave and how they react.
Exactly, and depending on the project, we might be interested once in medical applications, another time in pure nuclear physics, and another time in the nuclear reactors.
Okay, we've got another question from Corey on Facebook. Corey writes, could you talk about some of the other low energy experiments, such as the laser spectroscopy program?
I'm afraid I'm monopolizing. I don't know Corey, just to say. There's not a friend of mine who wants to ask me questions, so thank you, Corey.
Hey, Corey, thanks for watching.
I love the lasers. This was my PhD thesis. So what I also love about it, as I mentioned before, is you're talking to the atoms, because with laser light, you do not have enough energy to excite nuclei. So you're actually talking to the electrons, yet it's all interconnected. So of course, the electrons, they do see that there is something in the middle, which has the electric charge. They also can feel the size or the deformation of the nucleus. So by looking at tiny differences in the transition energy, so you're shining in the laser and then you're looking at the response, and one isotope will respond at this frequency, another isotope of the same element will respond at almost the same frequency, but maybe tiny different, maybe something like 1 part in a million or maybe in a billion. These are the small differences we want to measure. Once you have the difference, you fit it into a small equation which has several unknowns, and two of them are connected to the shape and also to the arrangement of neutrons and protons, what Liam was mentioning about neutrons and protons being in different orbits. And this is what you can get out just by observing the response of electrons to light.
Okay, so the electron is basically the messenger in this case. So you hit the
Exactly.
electron with the laser, the electron gets excited, but it moves based on what it's attached to, what nucleus it happens to be orbiting.
Exactly.
Okay, is that how you're able to find all these crazy shapes of nuclei?
No, not only. We try to do it, but I think Liam has a much better answer for that. How do we find it?
Well, that is one of the ways, and it's actually very complementary that we can use different techniques with the beams here, with many different experimental stations that we have. We have 10 permanent experimental stations, for example, and some that come on a temporary basis. And with that, we're able to actually study the same phenomena, but with different techniques. So for lasers, yes, you can also study the shape of the laser, because the shape of the nucleus, because it perturbs the energies of the electrons, like Magda just said, but also from reactions. So when we make a reaction, depending on how it reacts and how often it reacts and in which angles it scatters off the target, for example, then you can deduce the shape. So that reaction process depends on the shape of the nucleus.
That's so cool that we're actually able to look into atoms and see what the nuclei always look like, because in my chemistry classes, where I just do the nucleus as a circle, like here's the nucleus with a positive charge or with a neutral charge, and here it's the electron cloud around it. I guess it would always have a positive charge, right, because that has protons. We've got another question from Facebook. This is from Oscar. He writes, are there any applications in security?
I saw another question passing there just before, which was about the future of ISOLDE. And I like that very much because
we'll get back to you, Oscar, but we're going to ask another question that came a little bit before.
It's just to tell you, I think there's still a very bright future for ISOLDE. We have many ideas also what we can do to improve this machine. We are looking now, Liam was telling you all the applications, the things they are doing with the high ISOLDE. Let's say the upgrade of the energy so far. There we have now the new LINAC in place with cryo modules that contain the superconducting cavities. The idea is also perhaps in the future to replace the existing warm cavities that are still part of the REX LINAC, which started as an experiment but is now running also as a production machine, if you want, to replace those also by superconducting cavities in the same way as we have now the upgrade for the high ISOLDE. And also we're even thinking of perhaps in the future a storage ring where we could actually increase the intensity of the very rare exotic isotopes. There's many ideas still going on, so I think the future for ISOLDE is still very bright.
Because there's still a lot to learn about the nucleus.
Yes, I'm not wearing shades yet, but it is bright, the future. No, and I don't know the question on here on if there's applications in security. I wouldn't know. I mean,
I would just say, for example, the detectors that we are using, they might be, or also dosimetry, so that means measuring the doses that one can get. They might find applications, for example, then in airports, this kind of things. That if you have a very good detector that works with detecting less radioactivity than before, this might be used in these kind of things.
So you can look even lower limits than what we're capable of doing.
Exactly, and then if there's somebody smuggling indeed a nuclear weapon, then we would know it.
So we've got a question coming from Twitter from Sphere Charles. He asks, where is ISOLDE going next? And you said a little bit about that, but can you give us
I think
more of an overview?
No, well, the next step is now to finish actually the high ISOLDE project, which means, first of all, we're going to, next year, the coming year, we're going to put the fourth superconducting cryo module in the LINAC, which increases then the energy to 10 mega electron volt per nucleon. After that, we still have, of course, the intensity upgrade, and that becomes very interesting when the CERN LINAC 4 comes online. This is a study at the moment, and we will have to do a lot on the side of the target zone and the targets to actually make use out of the new beams coming from LINAC 4. So that's the direct future, and the other, well, the far future is what I already told you just before. Yeah.
All right, and our last question, this is from Rob. Rob asks us, what is your favorite isotope and why?
We go everybody.
No, I have no favorite isotopes. I love them all.
You love them all equally?
Every isotope. All bad. My favorite is magnesium-31. This was my thesis topic.
But you have to tell us why.
Because it has unexpected properties. Everybody thought that its spin is 7/2 of 3/2, and people were almost betting on it. It turns out it was 1/2, which we immediately saw by doing laser spectroscopy. There were 3 peaks instead of 4 that we were searching for, and now we have an explanation for it. There is not 1 neutron, but there are 2 neutrons which are just going up to the next orbit. And this gave us a physical review paper, which has been cited for over 100 times. So I like the isotope a lot.
And you did that as a student?
I did.
Well, congratulations.
Thank you.
My favourite isotope, well, today at least, is 108 tin, because that's the isotope that we're actually studying right now today. So I have to. Of course, it's my favourite. And my thesis was on 224 radium.
And it got him into a Nature paper on the front cover.
But you have to tell us why, and it can't just be because I was on the cover of Nature.
Because this is as a pear-shaped nucleus, and it's a very exotic shape. To really observe that online here at ISOLDE was quite cool to really see that appear from the data.
All right, well, thank you all for joining us today. Just to summarize and recap, today is ISOLDE's 50th birthday. So if you can't get enough nuclear physics, you want to learn more about the exciting research happening here, go on CERN's website, go on YouTube. But there's a new video series that just was posted today. We'll have articles coming out all week. And if you just love the research happening at CERN, you can't get enough, in a few weeks we'll be doing a Facebook Live at the CAST experiment, which is a telescope that looks to the sun to try to better understand dark matter. So that's coming up in a few weeks. Once again, thank you all for joining us, and happy birthday.
Thank you.
Thanks. All right.